Hello, everyone, and welcome to today's graph reading group.
Well, we have Minjie Wang talking to us about DGL and the release of DGL 1.0 and answering my maybe a little bit critical questions, but he answers them excellently. And I can tell you, this is pretty nice. You should check out at least the DGL 1.0. So let's go.
All right. Okay. All right. Thanks for having me here. It's my honor, actually. This is a great reading group. I actually learned a lot from the past talks as well. And my name is Minjie Wang. I'm currently a senior applied scientist at AWS Shanghai AI Lab. I got my PhD in NYU, and my major interest is in actually machine learning system. And I'm also the founder of this project called Deep Graph Library DGL. And I will be talking about actually, so here is my outline. Not the first slide, by the way, the second slide. I will talk about what is DGL, and also, of course, the new release, the exciting new release DGL 1.0, some of its highlights and why we are doing so. This is very important and why we think it matters for the general community. And second, I will also quickly actually illustrate some of the research work we've been doing here in AWS Shanghai AI Lab, and on the topic of GNN scalability, of course, very important for large graph, and also how to improve GNN with an energy enfolding perspective. All right, okay, let the journey begin. So what is DGL, right? So for people who haven't heard about DGL, Deep Graph Library, it is an open source framework for deep learning on graphs. So it actually was released at New Year's 2018. So it has been a couple of years, like so almost 4 years actually, almost 4 years. And it is initiated by NYU and NYU Shanghai. So I was actually developing it back to the PhD study at NYU. And later I joined AWS AI Shanghai Lab, so it is also currently maintained by the team as well. So it has become one of the most favorable frameworks by both academic and industrial users. You can see there are a lot of GitHub stars, forks, and also paper citations. I know, like we just talked about this, many of you have been using or are using DGL. Thanks to you so much for supporting us. And also you can see on your right-hand side, when we released DGL, there have been a lot of great responses from community and testimonial from different well-known researchers like Yang, like Xavier, like Thomas Keefe, the inventor of GCN. So they all like DGL, and that's why, and they keep us working harder to make the tool much better. So why you should use DGL essentially? What is the key feature of it? I will summarize it into 4 aspects. One is, first of all, easy to use. We provide a very unique graph-centric programming abstraction for users to express key operations like graph manipulation or like message passing. And also, the second one is the efficiency. We have a lot of underlying optimization, the system level optimization, such as fused message parsing kernels or IO optimizations for faster training, especially for larger graph. And the third one is scalability. We support training on multiple machine, multi-GPU. One of the unique framework out there, open source framework out there that can support that. And it can scale to graphs of billions of nodes and edges. And then finally, as an open source software, we also care a lot about ecosystem. We are happy to see many great actually open source works building upon DGL. And also we are happy to contributing and supporting them back. So let me quickly go through these 4 aspects one by one. First of all, the API side, as you can see on the left-hand side, this is a very simple program, just how to implement a graph convolution network in DGL. You just call in, let me use the laser pen. You just call the built-in GraphCom module, and you can see you can use it like a PyTorch module, and then do the forward function, pass the graph object, and also node feature into it, and get the convolved the new node features actually. And so you can see here, G is actually one of the core data abstraction in DGL is called a DGL graph. It's a graph object, And because there's a graph, we also provide many different graph APIs, such as graph construction, manipulation, sampling operation, traversals. These are actually naturally accompanied with the concept of the graph. And more than that, we also support a more complex graph like heterogeneous graph, and also to make it faster, many of these operators, almost all of these operators actually have GPU acceleration. Efficient runtime. So we know that message passing is very important for graph neural networks, and actually it is not a very great pattern for GPU. So we need to put a lot of effort to actually accelerate it. And in DGL we have this. This is our first. We first announced this design called fused message passing. The idea is we fuse the message phase and the reduce phase so that you don't need to generate any intermediate message tensor, which is of the size of number of edges in the graph, which is typically much larger than the number of nodes. So by using fused message passing, the memory complexity of a graph neural network is big O of the number of nodes in the graph instead of number of edges. So that's why it's very efficient. And the other part we have been focusing a lot recently is the mini batch training. As the graph is very large, you typically cannot fit it in the one GPU memory. So you need to have the mini batch framework. And also the mini batch framework actually incurs a lot of IOs, fetching feature data, for example, from CPU to GPU. And this calls for more efficient IO-friendly infrastructure, which we actually leverage CUDA UVA for this purpose. And this is also a collaboration project with many actually partners, for example, NVIDIA, Intel, and also like academic partner like UIUC and NYU. So it is actually a joint effort. And also this is why we're doing open source. We are working together with a lot of teams to actually present the best tools for everybody. And distributed training. Distributed training is also the key feature of DGL, of course. It supports multi-machine, multi-GPU. And also we want to keep the user experience simple. We want to make it similar to the single GPU training as well. And it supports graphs of billions of nodes and edges. Just give an example, like how fast is it to train, like, for example, a graph stage model, OGB paper 100 million. It only needs like 4 minutes to train that model using 64 GPUs, 8 machines. On 8 machines. So it is extremely fast because we did actually a lot of IO optimization and communication, like asynchronous communication, this kind of like low-level system optimization. And finally, the ecosystem. The ecosystem is also a kind of important aspect of the DGL open source package. And you can see there are actually a bunch of different like open source package built upon DGL or have a nice interface with DGL. To highlight a couple, for example, visualization, there are GNNs, I think developed from by Hong Kong University, graphics tree as well. And for complex graph like heterogeneous graph, there's an open source package as well called OpenHGN, which is a model zoo of heterogeneous graph. So if you want to, for example, find models that work out of box, you can go there. It is entirely built on DGL. And also Graph for NLP. This is a nice package about how to use graph neural network in NLP tasks. And it is also entirely based on DGL. And finally, we know that a lot of graphs are actually designed for AI for science. This includes like chemistry or bioinformatics, and DGL is also one of the models in the DeepChem package, which is also typically used by many bioinformatics or scientists. So you can see there is a huge open source community surrounding DGL, and it is also growing as well. And of course, all these things cannot happen in one night. Yeah, go ahead.
Yeah, before we get to that, about the efficiency thing that you pointed out, like, for example, or not what means, for example, just a question. I had these graphs where I have a set of nodes for one graph, a set of nodes for the other graph, and I needed to pass messages between them, and really between every single one of them. So it's like like a dense graph, right? But I also had multiple batches of these graphs, like a multiple of these graphs in one batch. And then what I did was, or one version of what I did was to just then take all of the nodes and basically build the whole matrix of interactions, or calculate the whole matrix of interactions, and then only take out or only pool together the ones for the graphs that belong together in that batch, right? And like I just did that in TensorFlow, in PyTorch, and without anything of DGL. And then the other thing I tried was having heterographs, where I have this or my single graph with this type of nodes and the other type of nodes, and I also had cross edges between them. And having these cross edges and then doing all of the stuff was far slower and took much more memory than just calculating this huge matrix with everything in my batch. So why is that?
Actually, so for that particular case, it is very similar to transformer, right? Because you can think about, you have different lengths of sequences, right? Your input data is different lengths of sequence. You want to calculate like self-attention, right? Pairwise self-attention.
Yeah,
so
right.
Essentially it becomes what you said, right? And so that's why I think if that is the case, the way typically people will solve it is just by padding. If your graph size is not like have too much variance, you can do padding or like bucketing to make each batch more efficient, to have less padding essentially. And the reason why we think this is, I think this is the right way to go actually, is because the pairwise attention is dense. It's dense, and if we use the sparse way to do that, like for example, compute, like use the second method you mentioned, right? Like construct a heterogeneous graph and use sparse way to do that, it actually calls into the sparse implementation, and which is not optimized for this kind of pattern, right? So in my opinion, I think this kind of approach, like this kind of pattern is indeed, your first approach is indeed the right way to go.
Okay. Well, fair. Okay, then I wanted to ask about the what you're pointing out, the nice community that's behind DGL. So to me, the most important thing about the community is like having a good documentation and having many Stack Overflow solutions, so to say. Like if I run into a problem, I just search it up in Google and then find someone else who had the same problem, and nice, someone answered it. But that was actually the main reason why I started using PyTorch geometric instead of DGL, because whenever I had some issue with DGL, it took me forever to find the solution, because I didn't find any like Stack Overflow articles or people solving the, and also I found the documentation very inconvenient. I don't exactly remember the reason why I found it so inconvenient or so bad, but I just found the documentation of PyTorch geometric much better. So have these two aspects changed by now? Would you say there's a reason to that? Would you say there's no reason to that? So yeah.
So actually, you give a very good, like I would say, critical feedback of DGL. This is actually exactly what we want. So in the later, I will talk about where can we find us. Like we actually have a team actually supporting the community. If you have questions, you can find us on Slack, our Discuss forum, and we'll answer that very immediately. And this is one channel. But of course, we want to ensure that even if you don't find us, right, you can solve the problem by just looking at documentation. Documentation is very important, like you said. So that's why we actually are collecting this feedback. Your feedback is very important, actually. So probably we'll follow up with you further about, okay, what are the documentation page you feel that you have blocking you from using it, and this is where we will actually improve continuously. And we also design a survey for that. But again, like let's follow up further on what exactly the problem is. We are very happy to hear this feedback and try to improve it.
Awesome. So you actually have a Slack where people can just write their problem in there.
That's right. That's right.
Awesome.
Yeah.
I think, yeah, so everyone here, if you don't know that Slack like me, probably very good information. And we already have in the chat, please share where we can join the Slack community. I think, Minjie, would you be, I mean, you're also in our Slack. It would be great if you leave a link to that, to your Slack there, so people can use that.
I will post all the information where to find us like later after the talk to the slide.
Yeah.
Cool. Thanks for the question. I like your question. Like, this is exactly why we are trying to talk to the community. Yeah.
I mean, I'm not trying to hide anything. Like, I'm just saying what I'm doing and what I like and what I didn't like. And I mean, my judgments, they weren't any sophisticated judgments, right, about the software or anything being better. I'm just one user who has this very subjective, uninformed experiences. Anyway, let's continue.
Let's continue. All right. Okay. So we have been talking about DGL. Like, it has been a long history of releasing different features. So we actually, to announce DGL 1.0, actually, the arrival of DGL 1.0 was last month in February. So it has a bunch of new features, actually, also a lot of updates to existing components. So here you can see this is the DGL 1.0 architecture. You can see there are many updates in, for example, at the front level, we have more models, examples for you to, for example, to work on edge prediction, graph prediction, explanation, more examples for you if you wanted to just learn or like using examples out of the box. GN utilities, more like NN modules, commonly used NN modules developed by researchers who put them into out-of-box APIs for you to use. Distributed training, also a lot of enhancement on the graph partitioning pipeline. And one of the most important feature is the introduction of the new library called DGL Sparse, which actually added the new data abstraction DGL Sparse matrix, diagonal matrix, and also a bunch of sparse operators into the library. So this is also what I'm going to talk about highlight in this talk. And maybe you guys will wonder, like, okay, hey, Minjie, you just talked about DGL. One of the key features is graph-centric programming. When talking about a sparse matrix, like in the new release. So here I actually quote one of the quote from one of my favorite movies, Arrival. Actually, it is a movie about one linguistic, Louis Banks, saving the world from aliens. So it is the central message of it is about a theory. A theory is that the languages you speak determines how you think and affects how you see everything. So this actually applies to, intrinsically, actually applies to GNN as well. So what are the language we speak in the world of GNNs? First, of course, the famous message passing view of when we describe a graph neural network. So if on your left-hand side, you can see this like famous equation. This equation describes if you want to compute the embedding of node I, there's an aggregation of its neighborhood. For example, one of the node is node J, and how we generate messages from node J to node I using this message function phi. So this actually equation describes the message passing like perspective of the graph neural network. And it is a local perspective because it describes it models how the node and edge computes, how the messages are passing along the edges, right? And because it's very local, so it lets people naturally connected with some other like famous algorithm like WL test. So you can see on your right-hand side, this is the illustration of WL test, which is also based on aggregating information from the neighbors, gathering information from neighbors and aggregating them and relabel them and do that in an iterative way. And you can see the strong connections between the WL test and the message passing paradigm just by looking at the equation itself. And this is why it leads to the famous paper called How Powerful Graph Neural Networks, which describe the expressive power of these message passing operators. So this is one of the language we are using. What are the other? The other is, of course, the matrix, because we can treat a graph as a sparse adjacency matrix. So that's why we can also treat a graph neural network as a function of a sparse matrix A and a dense tensor, which is a packet which packs all the node embeddings. And by formulating this, the graph neural network essentially becomes a series of operations, like maybe algebraic operations among these sparse and dense tensors. And by studying the property of these tensors and this computation, it actually leads to some interesting findings, like the over-smoothing problem, where it talks about how the features will become when you have a large number of layers. And this is the benefit of using the matrix view. It provides a global perspective, and it lets you easily to leverage the tool of linear algebra. And you can see like these two views and these two languages are complementary. They provide different insights into graph neural networks. And that's why, you often, when you grab a paper, a research paper from the graph neural network domain, you will see actually some people using like message passing formulation, some people using matrix formulation because they focus on different aspects. And sometimes these apps are actually interchanging. For example, if you look at the GCN model, the left-hand side is a message passing view where it describes how the node embedding I is being updated using the data from J and I itself. This is a message passing view, where on the right-hand side, this is totally mathematically equivalent how we calculated the new node embeddings using the diagonal degree matrices, a sparse adjacency matrix, and some operations like inverse square root. And here below the equation, you can see the code, how you can implement these two kind of perspective using DGL. On the left-hand side is the message passing perspective. In DGL, you first attach this data to the graph object. It triggers the update operator and pass it with the message and the reduce function. It will compute the message passing for you and generate the updated node embedding. So this is a message passing view. On your right-hand side, this is actually a teaser of the new DGL Sparse package. You can see the input is adjacent matrix A and X, and it first compute the diagonal matrix is inverse square root, do a bunch of matrix multiplication, and then compute the output. And you can see sometimes the graph neural network expressed in the matrix view is much simpler than the message passing view. And this actually motivates us to develop this package and release it in DGL 1.0. So DGL Sparse is a new sparse matrix package specialized for graph machine learning. We'll talk about that later. And to accompany this release, we publish 5 tutorials, all playable in Colab, of course, and also 11 examples with a focus on 3 training GN families: the graph diffusion-based GNNs, hypergraph neural networks, and graph transformers. And we'll go to these examples one by one. The first one is graph diffusion-based GNNs. So what is graph diffusion? It is actually a process of smoothing node signals by propagating them along edges. For example, if you look at this animation, you can see the node signals from one node, how it propagates through the network and smooths it out. So this is a very like useful mechanism to be used when we design a graph neural network. One very successful example is called predict and propagate, or APPMP model. On the right hand side, you can see the mathematical formulation of APPMP. So it first calculates a Z0 is the node embeddings in the first iteration from, for example, MLP model without any involvement of the graph. And then using an iterative process, calculates the k+1 by using the k and the Z0. So it becomes an iterative process, and the backward propagation will also backwards through this process as well. So below you can see the code of how to implement APPMP using the new like DGL Sparse API. You can see how it nicely corresponds with the mathematical equation. You first get the Z0, and then you have a number of hops, how many hops you wanted to propagate these signals. And then you use these like linear algebra to implement the iterative process. So this is for graph diffusion. The second type of family we found that is typically benefited from the sparse API is the hypergraph. So you can see here, hypergraph is actually is a generalization of a graph where an edge can involve more than 2 nodes. Here you can see an example. One edge, for example, E1 has 3 nodes actually, not 2 nodes. N2, N8, and N4, they all connected with each other on one edge. And hypergraph is actually very useful. So in the real world application, for example, on a commercial platform like Amazon, typically user will buy products like buy commercials like goods in many goods in one go actually. So this and we wanted to model this co-purchase behavior, and this naturally becomes a problem on hypergraph. And you can imagine, like, because hypergraph is a higher order relationship, it represents higher order relations than pairwise relationship. So it is very difficult to represent it as an adjacent matrix, because adjacent matrix essentially represents a pairwise relationship. So what people usually use is using incidence matrix, where you can see here is an example of the incidence matrix. The rows representing the set of nodes, while the column representing the set of edges. And whether the node, the 0, 1 means whether the node is incident on that edge. For example, you can see here E1, because it connects to N2, N8, and N4. So there are 3 1s in this column. And by doing this, we can represent a hypergraph. And because like the hypergraph is typically represented in an incidence matrix, when we design a hypergraph neural network, we will also utilize incidence matrix as a part of the component. So here is a typical example called the hypergraph convolution, I think designed in 2019. So here you can see the edge is the incidence matrix. And there are also like diagonal matrix DV and DE. They represent node and edge degree respectively. And the diagonal weight matrix W. And you can see the whole convolution operator is a bunch of matrix multiplication of these matrices. And on the right-hand side, you can see how we can implement it in DGL very nicely, just in a couple of lines of code. First, you compute the degrees of the vertex degree and the edge degree using the incidence matrix by just aggregating them on different dimensions. And then you create these diagonal matrices using the DGL Sparse.diag, and do the inverse square root, the normalization factor, and then calculate. Here we are using identity edge weight, and then you can see we just do the matrix multiply just like the equation, and you get the final answer. So you can see why the API is trying to map with the mathematical equation very nicely. And the final important family is graph transformer. So transformer, we know, has been like dominating in NLP domain, and the people are using it for graph as well. So one very like early, I would say, pioneer work of graph transformer is called like actually graph transformer. So so the idea here is, you can see if you look at the normal transformer, it access a positional encoding and then go to a multi-head attention module, and then go to a bunch of feed-forward network and do that over and over again. In the graph transformer, instead of using a fixed positional encoding, you will usually calculate the positional encoding from the graph. And then during the multi-head attention, will also incorporate the adjacent matrix to try to, for example, limit or constrain their attention along edges. So here is the more detailed mathematical formulation of the graph-aware, like a graph-aware sparse attention. So here you can see on the equation above is the normal attention equation. You have the Q and K, the query and the key tensor, you dot product them, and then do a softmax and multiply with a V. This essentially gives you the attention, right? And for the graph-aware sparse attention, it actually will element-wisely or multiply a sparse adjacent matrix A. So that means all the edges, well, you know, for pair of nodes, for the pair of nodes that form an edge in the graph, it will calculate the Q and the K dot product. Otherwise, it will just ignore them, and this becomes essentially a sparse attention mechanism. In DGL, actually, we provide operation to support this kind of in HPC domain. This is called sampled dense matrix multiply operator, and that's why we use the same name SDDMM here. And you can see DGL Sparse provide this operator to support them with Q and K transposition and A as well. And the nice thing about this operator is that, first of all, it supports edge weights that go beyond scalar. It supports vector shape edge weights. This actually makes it very easy to support multi-head attention instead of just one attention. Second, it is highly efficient because the underlying kernel, like what we did for the fused message parsing kernel, we will actually fuse them so that the general memory complexity will not involve any factor related to the number of edges in the graph, as it will only be related to the number of nodes. So here you can see the sparse matrix, sparse multi-head attention can be implemented in just tens of lines of code very easily, and also reads very well. Okay, so seeing all these examples, hopefully you agree that this new sparse matrix API makes the programming of this matrix view models much more simpler. Actually, we also have some measurement. For example, the average code reduction is 2.7x compared with DGL 0.9. And because of the underlying system optimization of these kernels, the training speed is also much faster compared with the older DGL and also versus PyG. A natural question left is, okay, now DGL has both support graph-centric message parsing, node-wise, edge-wise message parsing, and also matrix operation, which you will choose when you actually implement your graph neural network. So our principle is you choose the language that the model speaks. Essentially, if you are working on matrix models, matrix-based models, use the matrix APIs. Otherwise, you can use the message API. We give you the flexibility and don't worry about efficiency because underlyingly they are using the same set of kernel, so the efficiency is always great. Okay, so that's actually the part of the DGL 1.0, although I can take some questions in the middle before I go to the research part.
Yeah, thanks a lot for the presentation this far. I think it's really great to see the things that have improved, and especially I like the matrix notation, the matrix notation that avoid using all the updates and the message and things like that. Of course, in the field where I am, which is molecular graphs, because we rely so much on edges, I won't be able to use this. I will have to stick with the message passing framework so that we can embed better the edge features. But I remember a few years back, this kind of notation would have been definitely much more helpful than using the message, the updates, and things like that. Here you provide also simpler and faster. I see that. For example, on Cora compared to PyG, the training speed is similar, whether on it's similar except for sign. Whether on OGB archive, you get a higher speed up. So my question is why do you get a higher speed up on archive than Cora? In what kind of graph do you think that makes sense to use DGL in terms of speed and performance? What about small molecular graphs, very big dense graph, very big sparse graphs, very small dense graph? Can you tell us a bit more, and do you have more of these plots available?
Yeah, so we actually point out a very I would say difficult problem for the graph domain, because you have so many variants of graph in the world, right? So basically I have a short answer for that. If you have a large graph, right, DGL is the framework of choice because we have a lot of optimization for that. But I also wanted to touch base on a lot of technical aspects, so you will be more convinced. Essentially, like the key kernel optimization in DGL is try to avoid the instantiation of any tensors or memories associated with edges, like intermediate, not the like user provided edge features. If we can avoid that, then the memory saving and also associated memory bandwidth saving will be huge. And this is where DGL is focusing a lot. Like that's why you can see on small graph, it doesn't matter because all these kernels are run like, so it's basically framework overhead. While on slightly larger graph and also denser graph, especially on denser graph, you will see huge performance difference, especially for like models like GAT, because you associate a lot of like intermediate edge tensors, because you are calculating attention, right? So for this kind of model and this kind of like denser graph, DGL will have a much larger winning margin. So you will see that. And this is where we are focusing on. And we also like plan to do a lot along this line as well in the future. We wanted to see whether we can focus on PyTorch 2.0 to optimize it, like even going further using compiler techniques. So yeah, again, like hope I answer your question.
Yeah, it mostly answers my question. Now I know this presentation is more about DGL, so you don't need to go too much into the details, but I know that PyTorch Geometric 2.1 also implemented many of what you mentioned here, many of the techniques that you mentioned here, and also claimed that right now they are 10 times faster on Cora than they used to be. So like, do you have an idea like on what they did versus what you did? You don't have to go too much into the details, and you can focus more on the DGL side.
So essentially, I would say Cora. First of all, I would say Cora is. I know I'm using Cora here, but I would say Cora is L-form like benchmark in a way because it's too small. And I'm using it here mainly because I want to show that the simpler code leads to less framework overhead, which is also one of the pain points of DGL. By using this simpler API, it becomes negligible. And I would say the most important aspect is when you're going larger, when the graph cannot fit. Actually, I will talk about one of the research work later, is when the graph cannot fit into your GPU memory, how can we deal with that? For the domain you are working on, like multiple molecule graphs, the key problem is how you batch it. This is very difficult, and how to optimize for the block diagonal graph. This is also another topic. I think we haven't put a lot of effort in it yet, but of course, if we hear a lot of feedback from the community, we will work on that.
Yeah, okay, thanks a lot. Alec, maybe you can ask your question.
Yeah, I think you were just about to, maybe you're going to touch on this later, but I'm curious, you talked a lot about the underlying kernels for like the forward pass in a lot of these GNNs, but I'm curious about DGL's ability for like the node sampling and graph traversal algorithms.
Yeah,
because PyG's also worked a lot to speed those up on CPU and GPU. And so I'm working a lot with bigger graphs now, and that's one of the concerns I have. So I'd love to hear more about like how DGL compares with that, and also if there's any sort of abstraction to hook into graph data stores.
Yeah. That's great. Actually, this is what we are working on this year. Like external graph storage, external feature storage, and also like integrated with different pipelines that generate samples. This is something that we are definitely working on. And I will talk about the research work going forward is more from the, I would say, algorithm and system co-design perspective, but I'm happy to follow up with you for more information to share with you, like for example, compiler, how we optimize it, and also like the detailed IO pipeline, how we optimize the data transfer. These techniques, I can share more information with you.
Thank you.
Okay, so maybe let me move forward because I only have 20 minutes, right? Like, it's 1 hour.
Yeah, I mean that sounds good, but we're all excited to get into some research videos.
All right. Okay. So I will talk about two pieces of work essentially. One is about the scalability. The other is more about the modeling side expressiveness. So on scalability, yeah. So first of all, some stats. essentially we know that if we want to work on like public data set, right, large graph, so we look at OGB, like 240 million, that is the largest graph we have right now. Hundreds of millions nodes and billions of edges. It's pretty large, but not large enough, because what we are doing within Amazon, industrial size data is like 1000x larger. So it's still like trillions of edges. I'm not saying that we have solved that problem. We are still working on it. So we are also trying to see whether we can release part of the data set to the community to make like everybody can work on it. But anyway, before that, I just want to say like there's still a large gap and large space that people can work on large graphs. And the reason why I think the graph kind of like computation is very challenging, I wanted to summarize it using the unified perspective. So here, so let's look at example. So here you can see an example graph of 6 nodes, a bunch of edges, and to compute a graph neural network, right? So we can actually unfold the computation into a computational graph. So you can see here, the input I marked H0 is also the input feature X. And you can see there are a lot of like shallow, like gray lines. This is where you want to compute what are the information you want to gather in order to compute the second layer of the embeddings. So you can see the H1 here. And if we have 2 layers, this is 1 layer. If we have 2 layers, of course, we'll have like, we will stack that computation pattern again and try to compute the H2, which is the next layer's node embeddings. So now the problem becomes, okay, this is the whole computation graph of graph neural network. How can we fulfill it? And there are different strategies, and this leads to different optimizations. First of all, is the full graph training. So we know that in full graph training, we will compute everything layer by layer and compute all the nodes synchronously. So you can see here, if we want to compute H1, we will compute them at once and gather the information from H0, and then we'll move to the next layer to compute H2. So apparently, this will not work if you have a large graph, because first of all, it has a huge memory footprint. For example, here, if you want to compute this like in a synchronous way, you need to hold the entire the node embedding layers inside the memory, and this will become like unaffordable if your graph has like billions of nodes. And you can also think about, okay, why not we partition it, right? Why not we like, for example, offloading some of the data to disk or some external memory, and this essentially becomes a partition. So let me see whether I can do so. Yeah. For example, I can maybe partition the graph, right? I can first compute the left half and then compute the right half, right? But this actually is also problematic because of the data interdependencies. Essentially, you will have a lot of like communication between this boundary, and for a graph that has scale-free property, where one node may connect to a majority of the other nodes, this communication becomes a severe bottleneck for the pipeline. So this is full graph training, and to actually solve the problem of the huge memory footprint, people have been thinking about, okay, hey, why can't we like train it in a mini batch way? So let's look at mini batch training. So what is mini batch training? So first of all, we will select a node, for example, node 1 as the batch 1, and then we figure out this computation dependency, right? And because we have 2 layers, we need to figure out the next layer as well. And then after we figure out all the computation dependency, we evaluate the computation graph from the bottom layer to the top. So you can see here, this is where these highlight edges are the computation graph you need to like evaluate it. And this is the first batch, and then we'll move to the next batch. For example, the next batch is node 2, and again we will try to find its dependencies, and then find dependency again using the recursive process. And finally, we get a full computation graph, and then we evaluate from the bottom to the top. So you can see this is like a mini batch training. Of course, it is better. It is a little bit better than the full graph training, because you are limiting the memory footprint of each batch. But again, it has a huge problem because of the neighborhood explosion problem, right? So you will have a huge receptive field, and it almost like touches all the nodes in this very simple examples for each batch. And this is also a problem. So to actually mitigate the issue, so people have thinking about, okay, why not we just do sampling, right? Like instead of, for example, looking at the entire neighborhood, I just look at a partial neighborhood, and by iteratively like looking at the subsets, hopefully we can approximate the neighborhoods during the process. So here is an example of node-wise neighbor sampling. We still choose node 1 as the batch 1, and we don't choose from the two neighbors, 2 and 6. We only choose one neighbor, one node 6 as one of the dependency, and then we move to the next layer as well, and we choose one of the neighbor as the dependency. And you can see this graph is slimmer. This computation graph is slimmer than the original mini batch computation graph. And we can also move to the batch 2. Again, we do the same process and get the batch 2 computation graph. So this is node-wise neighbor sampling. So it's still it is better than the planned mini batch data flow graph, but it still have neighborhood explosion problem. It cannot be avoided. And there are also other work, for example, like layer-wise sampling and subgraph-wise sampling to actually be more aggressively like pruning away the computation graph of each mini batches. But again, like this sampling may introduce some unintended structural bias. And so right now it is not clear whether the sampling method can be general across all the graph and all the algorithm. So this is like mini batch plus sampling. There's another line of work that actually try to mitigate the problem by using historical embedding. So here is how it works. For example, the batch 1, we still do the what we describe in the mini batch process. We pick node 1 as the first batch, and then we find the dependency, and then do that recursively find the entire computation graph and do the evaluation. And at this moment, because we use node 1 as the first batch, we will record this the embedding of node 1 and save it in the memory. And later for batch 2, when we encounter node 1 again during the neighbor expansion, instead of actually recursively try to aggregate this neighbor, we actually reuse the embeddings from the previous iteration. So you can see here node 1, it does not go to the 1 to 6 again. It just reuse what embeddings here. And then you can imagine that we can do that, so on and so forth, and hopefully to the eventually we'll compute the node embeddings of all the nodes, and to the very end of the batch, we will have the benefit of like having most of the nodes like their embeddings being recorded, so we can actually reuse them without doing neighbor expansion again. So you can see here, this is a computation graph of the last batch. In this example, and all its neighbors are being reused. This line of work actually has, I think back to 2018, there's a paper, there's a pioneer work called a variance reduction GCN, and there are also follow-up work like a GN autoscale and a graph FM. They are also actually following this kind of idea. So now the question is, are we good? Is this the solution we want? Actually solve the problem? So actually we found there are two issues when we apply these historical embeddings on large graph. First of all, it has a huge memory requirement. It is OLND for an L layer GNN with embedding size D on graph of n nodes, because you need to record, you need to save all the historical embedding of each layer, the node in each layer. So here you can see for this graph, you can see you need to store not only the import feature, but also the node embeddings here and here. Of course, you can put it like into, for example, larger memory, but slower memory, like CPU memory, or even on disk, build it on disk. But this again, like increase the I/O latency. So and there are also research will try to see whether we can compress them into, for example, a vector quantization. But again, this is still like a problem that this kind of historical embedding methods face. The second problem we found is that it on large, especially on large graph, it actually impacts the model accuracy by a lot. And the reason is because it may happen to use the very old node embedding like this one. For example, if you look at this example, when we work on the batch, the last batch, the batch that contains node 6, it will inquiry the historical embedding node 1, which is generated 6 iterations ago. So if you think about this as a very large graph, it will be generated in the beginning of the iteration while you have a lot of gradient update. So the embedding you generated in the first iteration is already drifting away during the update. So using that still embedding is very dangerous, and we found that it actually impacted the model accuracy by a lot. So you can see here, these are two actually examples. Here on a smaller graph like OGBN products, right? You can see roughly all these models are still very close to the target accuracy by neighbor sampling, but on a larger graph like papers 100 million, the accuracy gap is huge. Okay, so how we solve this problem? So I just briefly go through the idea because I want to, so for people who are interested, you can always refer to our paper. So first of all, history embeddings are great. So we still want to reduce it, but we should use it very wisely. So here is the experiments we did. You can see here, we measure the embedding distance, how the embeddings are evolved during the training iteration. So here different lines are actually at each iteration and its cosine similarity with respect to the iteration before. So we want to see whether like how the embeddings are evolving during the process, during the training process. And what we found is that for most of the nodes, their embeddings quickly become stable. So they don't change a lot, and these are the embeddings that are safe for reuse. But there are a small portion of the embeddings that are actually unstable. They change a lot. They have huge variance. We should avoid using them because they actually influence the model accuracy. So this is a statistics, but the challenge now becomes during the training process, how can you identify the stable embeddings on the fly? So we actually devised two strategies. One is for in-batch nodes, that nodes within the current mini-batch, we have the access to their gradient estimation, so we can use that to see whether the embeddings will not be changed by a lot in the future. And the other is for these out-of-batch nodes that we do not have access to the gradients, we can try their stillness counter. And for example, if it goes beyond a certain number of iterations, we just drop them, so we will never reuse them. And you can check out our paper called Refresh. This paper we archive. So the idea is we actually formulate these strategies as a cache mechanism. You can see like this is naturally a cache mechanism. We need to decide what are the embeddings to be saved in the cache and what are the embeddings to be evicted because they are outdated. And we found that using this strategy, it essentially prunes away a lot of computation because you can reduce historic embeddings, and also you don't have the accuracy loss. So we found that we can train this graph stage OGB and paper 100 million in 25 minutes using one machine, just one machine. And normally for neighbor sampling on DGL, it takes 2 hours. For PyG, it's more than 6 hours, and there's almost no accuracy drop compared with neighbor sampling. So, and it also works for heterogeneous graph, and it is, I was agnostic to what kind of a neighbor sampling you want to use. If you are using like sampling with bias, okay, you can still use this cache mechanism to accompany with you. So this is for the scalability side of work. And the second line of work I will talk about is improving GNN with an energy unfolding perspective. This is a work done by my colleague, David With, and and also a collaboration with many like Fudan University and KAIST. So what are the problems? So the problem we are tackling is the over-smoothing problems that we have been talking about. So when we stacking a large number of GNN layers, we know that because of the propagation property of these, like diffusion property of these graphs, so the features will become concentrated in a certain regime. So essentially, it becomes not discriminative, and you cannot use them for example, prediction. And the reason is, again, like I have mentioned that in the matrix view slides, it's because of like the diffusion matrix. If you do that over and over again, it becomes a global aspect, and there's no personalized like factors associated with each node. And there are also other consequences of like over smoothing problem, because we cannot use a lot of a large number of GN layers. It becomes difficult to track these long-term dependencies. And also, almost all the real graphs are noisy. So there are edges that are spurious, and they are taken by mistake. So for this kind of like for this kind of data set, if we cannot use like a deeper model, it is very difficult to capture actually these noisy edges. So how we solve it? So the way we do is actually we are tackling it from a different angle. So we formulate the optimization problem from the energy optimization perspective. So essentially, for graph neural nets, for the graph problem, we can devise an energy function like this. This is just one example of energy function. You can also choose other form of energy function. So here is the first term is capture the distance between the node embedding you wanted to calculate it between the base model, which is parameterized by W. And the second term is try to use the graph as a regularizer to smooth out the node embeddings you calculate. You wanted their embeddings to be close to each other once they are connected. And once we have this energy function, supposedly we can optimize it and get an optimal solution Y star. So we optimize this energy function at Y star, and then we know that okay, this Y star probably could be a very good candidate for classification problem. So we can feed it into another loss function that is for the classification problem. So that is for the classification problem. So the difficulty here is, how can we optimize the whole process end to end? Because you can see here, if we want to optimize this loss function, we need to backprop through the optimization process again. So it becomes a bi-level optimization process, and the challenge is how to optimize this. So actually, what we found is we can actually use an iterative process to unfold this optimization. So here is what we derived. You will find it very familiar, like very similar to like the APPNP model, because it also has this iterative process, like to compute the k step yk, you rely on the k-1 step, and also using the Laplacian matrix here as a diffusion operator on the yk-1, the last layer's node embedding, and here you can also see a skip condition from the base model. Essentially, by using this kind of iterative process, we prove that this actually optimizes what we see here, this bi-level optimization problem. And the interesting finding is, like, if we map this algorithm to GNN, we can see that each step corresponding to one GN layer. So you can think about this like optimization problem as a stack of GN layers. And by going through one GN layer, it essentially goes down to the like the optimization to minimize the entire energy. So essentially, this idea is to treat, like, to devise the graph neural network architecture from the energy function-based like perspective. And I just briefly go through the central idea. For people who are interested, feel free to actually read our papers. We have a bunch of papers. The mathematical formulation and the basic idea is actually done in this work called tools, and it also can include attention like variance as well. And then later we also extend that to the heterogeneous graph model, and try to, for example, and also try to connect it with the transformer model. And right now we're working on, for example, like extending it to the hypergraph. So one more thing about this line of work is, because it uses a lot of like these matrix operations, so it actually nicely maps to what the DGL 1.0 provides, the DGL Sparse package. So here you can see this is a very simple code, just how to implement the diffusion process in the Turos model using DGL 1.0 Sparse. And if you're interested, you can also check out the example. We actually include that example in this release. All right, okay. Looking forward, so I will do some conclusion. First of all, like DGL is an open source package, and we serve your guys, like the research community. So we wanted to enhance our user experience performance. For example, like Sparse Matrix API, if you have any requests, let us know. Message passing API, we also have planned to simplify it to make it more easier to use. And scalability, there is still an open question of like what is the canonical training paradigm for large scale GNNs. And a more complicated scenario is in real world graphs that we are dealing with within Amazon. All these graphs are heterogeneous, and they have like temporal information. They are also dynamic. So for this kind of graph, what are the canonical training algorithm is still a question. And for data, we are also looking at how the graphs are coming from. For example, like we see a lot of graphs are coming from tables. So we want to see whether there are tools or like algorithms that can automate this process. Again, if you have any like questions, so here is a QR code. This is a survey. This is a survey we send out to the community. You can scan the code and put your feedback there. And we will actually, if you are interested, we can also follow up with you. Or you can join our community. So here you can see all the bunch of like community portals we have. We have project page, GitHub page, and Slack. You can visit our Slack, and also Twitter. You can also follow our Twitter for the latest news. For Chinese, if you're using Zhihu, which is also like a Chinese Quora, you can follow our like Zhihu blog as well. We will post the regular news about DGL as well. So, okay, thanks everyone for listening. I'm happy to take more questions.
Thanks for the nice presentation and for sharing these resources with us. Yeah, I think it's pretty interesting. And I want, before I ask, let me get to some questions from the chat. Does DGL now allow modification of edges, adding/removing on the DGL.graph or DGL.heterograph data structure during training time?
Graph structure learning. Yeah, so DGL has this API called add nodes, remove nodes. So it allows you to essentially allows you to modify graphs as you wish. Yes, the answer is yes.
Okay. Then I forgot my question, but Pablo's writing excellent presentation, and that's true. Thanks. Dom, do you have any questions until I think of remember what I wanted to say?
I just want to say that it's a great presentation, and really looking forward to using DGL 1.0. I use DGL for years now, as I mentioned already. Yeah.
Thanks.
I don't have more questions, but if I think of any, I'll ask.
Yeah. Is there anyone like, when you have a PyTorch issue, something doesn't work, you go on Google, you Google your error or whatever, your problem, and then you find some Stack Overflow, and there it's always this Patrick BLCK or something like that answering the question, so to say. Like there's always this one guy who answers the question, or there are multiple people like that who are super involved in Stack Overflow and answering questions of people there. And is there also like the DGL person, the DGL version of that, someone who answers all the questions on Stack Overflow?
Yeah, so this is one thing that we miss actually. We usually keep track of, so there are two channels we usually listen to, three actually. One is Slack, one is GitHub like issues. The third one is Discuss Forum. So these are the three like channels we usually watch for user questions. But Stack Overflow is not one of them. So this is actually very great. This is something I want to pass to my team. We actually look at all these questions weekly, and I ask everybody, don't overlook every single question. Please answer them like as soon as possible. Be the owner of the community. So yeah, Stack Overflow definitely something we'll check out later. See whether we can actually support them.
Stack Overflow was just an example, like GitHub issues. That's the
GitHub
same
issue,
to me.
Yeah, so we answer them very quickly. So if you found that, like we also track them, like this is something we will optimize, of course. And the thing is for DGL that we don't have a single person that answer all the questions. It's more like a teamwork. So you will find that, okay, maybe this week is this guy, maybe next week is the other guy. Yeah, and that happens.
Yeah, I mean, it's just, I was curious if they are, like, for some, I don't know how this Patrick PBLCK or whatever exactly his name is, how he is, or if he's involved with PyTorch at all. But I just always see this one guy answering so many questions. Anyway, then so I just think it's nice to have something Googleable where the solutions come up. So something not like Slack, but I guess you have discuss DGL.ai, which will Google probably indexes and then sees whatever or has already been answered there, and also the GitHub issues. Google definitely shows those up if the problem has existed before. Anyway, Alec, what's your point?
Yeah, so I've been haven't been a big user of DGL, but I've been looking at some of the AWS blogs on using DGL for big data, and it seems like they most of their examples use MXNet as the backend, and so I was under the impression that DGL kind of has this like flexible backend between MXNet and PyTorch. I was wondering if you could comment on that, because everything you've talked about today is kind of from the PyTorch perspective, which is great because I don't want to think about MXNet, but what's the deal with that? Yeah, so actually this is a question like, I would say this is an interesting fact that when we start this project, we wanted to, because we don't know. At the moment we start the project, we don't know which framework becomes the dominant one. But right now there's clearly a winner, right? PyTorch is dominating, right? So in the future, actually, we will double down on PyTorch, essentially. Like, for example, the Sparse matrix, the Sparse API library, we developed entirely for PyTorch. No other framework can enjoy that. And this actually gave us a lot of benefit because, for example, I think some people is asking questions about whether they can customize or has the flexibility to develop operators like in Sparse. That's totally doable because we are doing native PyTorch extension. You just follow the PyTorch the official tutorial. You will be able to do that in DGL as well. So we are no different than just any PyTorch ecosystem framework. And this also makes us easier to be compatible with the PyTorch ecosystem tools like compilers and other like Captain, these PyTorch Lightning, all these like ecosystem tools, because we are native PyTorch native right now. Yeah, and moving forward, we're also putting more efforts for PyTorch, of course. Yeah, we know like most of you are PyTorch users. Yeah, but if you are TensorFlow users, don't hesitate to actually leave us feedback on the survey. We want to show some love, but you need to let us know that you are using it. Okay, thank you. That answers my question.
Okay, so the guy that I meant, he's actually on the questions he answers are actually on pytorch.discuss or discuss.pytorch.org. So yeah.
I see.
Want to show that to me, I didn't even realize there's a different, or that's including different sites. Hao Teng, what do you want to say?
Yes, so I basically working on large scale graph representation learning. So I saw PyTorch Sparse, the DGL Sparse released the package. I'm really excited about this. So, but like my question is, how large graph can DGL Sparse support right now? because like it's kind of a trade-off, right? Like when you have a smaller graph, it's not necessary to use a sparse. At the same time, you may sacrifice some performance. For really large graph that you cannot fit into even the GPU memory, because I tried, like sometimes I can have a faster performance on the CPU side when the sparse graph cannot fit into the GPU memory. So how do you guys think about it in this direction?
Yeah. So the DGL Sparse is mostly created from the perspective of supporting like the API perspective, try to be more nature towards what the research is going towards. And for the scalability, like the sparse and the message processing or digital graphs, they're underlying using the same infrastructure. So the efficiency is the same. So for your question, when the graph is large, they cannot fit into the memory. Yes, and in this case, when you think about on the algorithm and system code design, like whether we can put some of the graph, for example, maybe even spill it into disk, and try to devise efficient or IO-friendly sampling algorithm to utilize the entire hardware, not only just CPU. So right now, the bottleneck I can see is if we want to work around, for example, 100 million, right? We need a machine that has large RAM memories that can fit the graph first, right? And this won't work if our large is 10x larger, right? So we need to find a way to actually. So my thought is we need to find a way to utilize this graph data structure in a more IO efficient way. Like right now, there are a lot of random access, like neighbor sampling, a lot of random access. So it is not great for the current hardware. But is there any IO-friendly way of doing sampling? I don't know. I'm actually keen to know as well. Yeah.
Okay. Oh, then one follow-up. So we know that the PyTorch or other libraries are really bad at supporting sparse operations. I know that DGL make the first step to make it better, but do you guys aiming at to provide the same support like doing things like a SciPy sparse, because right now a lot of operations are supported by SciPy and not is supported by the DGL. Yeah.
Right. So eventually our goal is we are taking the first step in the sparse. It's mainly because we have this requirement for GraphML. That's why I say it's specialized for GraphML, and it's not for general sparse. But what we wanted to do actually is we wanted to see whether we can incorporate our design into PyTorch sparse as well. We wanted to, so it's as an open source, we don't want to like invent the wheel again. We wanted to see whether we can make the wheel better, right? So we will also think about whether we can make PyTorch sparse better in this way, so that in the future, like everybody can use just one tool. You don't need to choose. I hate to choose for users, right? So that's it's still like a longer term. We will continue our path, but we are actually looking to see whether we can work with PyTorch team as well.
Okay, great. Thanks so much.
Also wondering how much attention you have for knowledge graphs.
Yeah, that's another interesting question. So the other question I have is, so right now we are mostly working on like this, I would say interaction graph in some way. Like if you think about recommendation, fraud detection, this kind of like application is more like interaction graph. Knowledge graph, we are not particularly looking at it, but again, the support is via the heterogeneous graph support, so it's kind of related. The other questions for the more general domain is like, given the rise of ChatGPT, whether knowledge graph is like a necessary tool is another question. I don't know. Like, so I would like to see more like inputs from the community. Like, for example, tell DGL, okay, what are the directions that we should move towards for knowledge graph?
Well, thank you everyone who attended in person here for these awesome questions, and to you maybe also joined for the next round in person. All the information is down there in the description, and also you saw all that information from Minjie, right? So if you're using DGL, join their Slack and ask them the questions if you ever run into problems. Use their help But I mean, apparently that's what they like doing, and that's just awesome. So big thanks to Minjie and the whole DGL team, and also to a big thanks from me to the rest of the whole community on machine learning research. It's awesome to have all of you people putting out stuff like PyTorch, answering questions in the community, and also you people being here in the reading group and being part of this nice community. See you.